Good morning, students. This is PURNACHANDRA Higher Secondary online classes. Okay. So in the previous session, we are discussing about the Gauss's law and the electric flux. In this session, we are discussing about the application of Gauss's law. So in the application of Gauss's law, the first application I have discussed in this clip or in this session. The first application is we have to find out the field, electric field, due to an infinitely long straight charged wire. It's very simple. That means we will take a infinite charged wire, as you have seen in this figure. Okay, as you have seen in this figure, we are taking this charged wire which is infinitely long. Okay, this middle one, clearly it is visible. Which type of charged? The positively charged. You can also take it as negatively charged, but we are assuming that let this infinitely long straight wire which I have taken, that is positively charged. Okay. Now what is our aim? Now due to this positively charged wire, we are finding out the value of electric field. That is a very important one. We are finding out the value of electric field intensity. That is our aim. Okay. So for which, that means where we have to find out the electric field? Now at some point. So let us take a point P here. So before that, you are very much visible here. There is a cylindrical shape of surface, a closed surface around the charge. What is that one? Let us discuss about that one. Okay. So in the previous session, I told you that to apply the Gauss's law, we must have a closed surface, and that closed surface is called your Gaussian surface. Okay. So remember, and a very important concept, due to a positively charged wire, infinitely, whether it is infinite or it is a finite, but due to a long straight wire, which type of Gaussian surface I will assume? A cylindrical type of Gaussian surface I will assume. Why? Because as you have seen, this is positively charged. That means from a positively charged straight wire, the lines of force, these are the lines of force. Okay, there are so many lines of force. I have drawn only few. So there are so many lines of force which are out from this surface, because as in the previous discussion, we know that from a positive charge, the electric lines of force coming outward, and from a negative charge, the electric lines of force becomes inward. Okay. So now, as you assume, suppose I will take, let us take a paper. Okay. Let us take a paper. This is your infinitely charged. Suppose this is your infinitely charged your wire. Okay. Then around this there are electric field lines are emerging from this outward. Okay. So now if I will circle it, then you will assume it is a cylindrical like surface which is closed from both sides. This side and also this side. Okay. So that means, remember that one, for a infinitely charged conductor. Okay. Charged, that is a very important one. Charged conductor, which type of Gaussian surface? Now a cylindrical type Gaussian surface I must take. Okay. So now what is our aim? Now from this or in this cylindrical type Gaussian surface, we have to find out the electric field intensity. So that's why, as we know that in a cylinder, there are two types of surfaces. One is your curved surface. This one is your curved surface. Okay. And this below one and the top one, these two are your plane surface. Okay. In every cylinder there are two plane surfaces. Okay, and this is your curved surface. Very simple, as we know that. So now, what we are assuming? Now we are assuming that in this Gaussian surface, this is your Gaussian surface. Again I will repeat. This is your Gaussian surface, and it is an imaginary surface. It is not a real one. It is an imaginary surface. Okay. So now in this Gaussian surface, I have to take a point P, and in this point P, I have to find out the value of electric field intensity. This is our main aim. So for this, what I will do? So I will take a small surface ds. Look at here. I will take a small surface ds here, because we cannot directly find out the whole surface as we have discussed. So for this, let us find out, or let us take two small surfaces. ds, this here in the curved surface ds, and this is your ds in this end. And you can take also this ds here also. Both result are same. Okay. So that's why any one of them you can take. Let us take this ds in the curved surface. this one, and this open surface let us take ds. This is very simple. Now, before going to the derivation, let us find out the direction of ds, because ds is nothing but a small area, and this small area is having area vector. So look at this. This is the marked one. Now what I have marked here? This marked surface area, small surface area ds, is having a direction in this, because to this surface, this area vector must be normal to it in the physics concept. Okay. So now this is the direction of ds, and you can see it from this charged, infinitely charged conductor. The electric field intensity direction is also outward. Very simple. So that's why this is the direction of ds, and this is the direction of electric field intensity. That means both are in same direction. In this ds, which I will take in the curved surface. But come to here. In this ds, which I marked here, the ds direction is also perpendicular here, but the electric field direction is in this direction. That means the angle between them is 90 degrees. Very simple. So in this case, the angle between ds and e is your 90 degree. But in this case, which I have taken in the curved surface part, the angle between ds and e, again I will repeat, ds and e, this is your 0 degree. Okay, because why we are going to take, or why we are emphasizing on these 2 points, that is electric field and ds, because before finding out the electric field intensity, we must go into the electric flux. And what is my expression of the electric flux? The expression of electric flux I have discussed in the previous class. That is phi is equal to integration over, as it is a closed surface. So let us take the closed loop. Okay. So integration, the formula E dot ds. That is important. That's why for this reason we are emphasizing on these 2 points only. That is E ds, and again this is d ds and e. This is the direction of ds here, and this is the direction of electric field intensity. So now in this 2 part we are finding out the electric flux phi. So phi is equal to closed integration over the surface E dot ds. Very simple. So now let us find out the total electric flux, or the total number of electric field lines over this curved surface and over this plane surface. Okay. So now first of all I will find out in this curved surface, or for this ds. So this ds means, let us find out this one. So integration over, so that is integration eds means E dot ds, so E ds cos theta. Very simple. So that implies integration E ds, the theta is, again I will repeat, the angle between E vector and ds vector. The angle between E vector and ds vector. So it is 0 degree because both are in same direction. So this is cos 0 degree. Okay. So that's why is equal to integration E ds, because cos 0 is 1. Very simple. So this is your integration. Now that is equal to, this is the over surface. That is equal to your which surface? Curved. So that is an important one. This surface is for the closed, your curved surface. This one, curved surface, not for these 2. So now integration E dot ds. So E I will take outside, integration over ds. Okay. So that is equal to integration, closed integration over ds. As you know, this is your s, integration of ds is s. Okay. So now what is the surface area of the, remember this s is the, again I will repeat, this s is the surface area of a cylinder. Which type of surface area of a cylinder? The curved surface area. Curved surface area of a cylinder. So what is the formula? Let us discuss here. So curved surface area S of a cylinder, the formula is, look at here, the point P is at a distance R and the length of the cylinder is distance L. So that's why the area become how much? The 2 pi RL, as you know that. So let us put it here. So this is E 2 pi RL. Very simple. Okay. So that is phi is equal to, what I will get? The phi is equal to E 2 pi RL. Okay. So let us write down again. So I will erase that one. Now finally, your flux across this curved surface area, how much I will get? Now E 2 pi r L. Okay. So now, so this is the amount of flux or amount of electric field lines or lines of force in this curved surface area, in this part. Okay, a cylindrical surface, curved surface area. Now I will compare this with the Gauss law because I have to apply the Gauss law. So what is the Gauss law? Now applying Gauss law. Applying Gauss law. Okay, so from the Gauss law you know that the flux is equal to the 1 by epsilon 0 times of the total charge enclosed by that surface. This is the expression that is from the Gauss law. Phi is equal to q by epsilon 0. In the previous video we have discussed that word. Phi is equal to q by epsilon 0. Q means the total charge enclosed. Now come to this. This is a very important concept, q. Okay, so here q means a point charge, but here we are not taking a point charge. We are taking a line charge. That means charge distribution. Which type of charge distribution? The line charge distribution. So that's why in place of so what is the value of q? Okay, so total charge. Remember the total charge q is equal to how much? How much? How to find out the total charge q? So q is equal to the line charge density. It's very important because for a line charge I will take a line charge density, and a line charge density is nothing but the charge, the total charge q divided by the length. Very simple. Okay, and our aim to find out the q. So q is equal to, now this is your lambda into what is the length of the cylinder? L is written here. The length of the cylinder is L. So let us so lambda L. So this is the value of total charge. Very simple. Okay. So now so q is equal to lambda L. Let us put the value here. So I will get q is equal to how much? Now lambda L. Q is equal to lambda L. So let us put this value in this part. So what I will get? Now the flux, according to the Gauss law, the flux phi is equal to lambda L divided by epsilon c. Okay. Now very simple. Now let us take this is equation number 1. This is your equation number 2. So I have to compare these two. I have to compare these two. So let us compare these two. So let us compare this equation number and equation number 2. So what? Let us compare these two. So by comparing this, I can write E 2 pi r L is equal to lambda L divided by epsilon 0. I have to compare this equation and equation 2. So that implies, what is our aim? Our aim to find out the electric field intensity. So electric field intensity E is equal to how much? The lambda L divided by 2 pi r L epsilon 0. Okay, so this L cancel out. Now finally, what is the result I will get? Look at this result. So the electric field intensity E is equal to lambda divided by 2 pi r epsilon 0. This much. Okay, so this is the final equation number 3, and this equation number 3, again I will repeat, the equation number 3 signifies, this equation number 3, whatever I have written here, this one signifies the total number of electric field intensity due to this infinitely charged wire. Okay, so from this we will get this electric field intensity. Now there is a question arises in your mind, sir, what about this ds? So let us discuss about this ds. Look at this. This ds, in this small area ds and electric field intensity, the angle between them is 90 degree. And here also, if you will take, you can also take here, there is a ds, and this is also the direction of ds, and this is the electric field intensity. Very simple. So what is the angle here also? 90 degree. Okay. So look at it. Look at it. So 90 degree. This is also 90 degree. This is also 90 degree. So if I apply this formula, this 90 degree, what is the flux? The flux is equal to, that is phi is equal to integration E dot ds. Okay, so that implies for this surface, this plane, this and this. Okay, so flux is equal to now E ds cos theta. And cos theta in place of cos theta, I will put cos 90 degree. Cos 90. What is the value of cos 90? Students, plus 0. So that's why for these two surfaces, that means this and this, we cannot consider the flux. That's why for these two surfaces, what is the value of electric field intensity? The electric field intensity value is simple C for this one. That's why you cannot consider these two. We only concentrate on this surface, that is curved surface, this one. Okay, so that is the final answer. So this is my final answer. Remember, students, that is our aim. What is our aim? Now we have to find out the electric field due to infinitely long straight charge wire at some point. So in this point P, whatever mentioned here, so in this point P, the amount of electric field becomes E is equal to lambda. Lambda means the line charge density divided by 2 pi r epsilon. Simple. Thank you, sir.